Okay, we're going to start a new chapter today. Our next unit is on exponents and logarithms. So today what we're going to do is we're going to look at to see what an exponential function looks like, how the equation works, and sort of what the graph looks like, and how you can answer some questions based on that. So the first thing is, what is an exponential function? It's typically in the form y equals cx, where c is just some constant number. So it could be an equation like y equals 2 to the x, or it could be something like, it can be between 0 and 1, less than 1, which would be like a fraction, like 1/2 to the x, or something like that. So what happens is, if c is greater than 1, what happens is our values are increasing. So in this case, if we have y equals 2 to the x, what that means is, for every increase of the x, we're going to double. So when x is 1, we get 2. When x is 2, we get 2 squared, which would be 4. When x is 3, we get 8, and so on. And if it's y equals 1/2 to the x, what that means is, as your x increases, we're going to be cutting our value by half. So in this case, we'd have, our equation would be, if we started with, say, 10, and then when the next x interval would be 5, and the next interval 2.5, and so on. So the graphs basically just increase or decrease. So a positive c value bigger than 1 would be an increasing graph, and anything less than 1 would be decreasing. All of exponential functions in this form all cross through the intersection point of y equals 1. And the reason for that is, if we put in y equals, our x equals 0, so we'd have y equals 2 to the 0 in this case, anything to the 0 is always 1. So we always get a y-interception of 1, and then we also see that our domain is any value, because the x direction goes on and on forever in both directions, but we see we'll never get it equal to 0. So no matter what x is, we can get a really small number if x is really, really small, but if you put in something like y equals 2 to the negative 100, you would just get 0.000. So you can see the graph gets really, really close to the x-axis, but it'll never touch, so therefore our range is always going to be bigger than 0. So what we want to do here now is basically we want to graph each of these functions, see if we can figure out what they look like. We'll figure out domain and range and all those things. So on your calculator, if you put in y equals 3 to the x, we would get our graph that does something like that. It's going to cross at 1, and when y equals 1, we'd be at 3. When y equals 2, we'd be at 9, and so on. So in this case, we'd say our domain is xer. Our range is greater than 0. Those are always going to be the case for these graphs. We have an x-intercept of none. There is none. It never crosses the x-axis. Y-intercept of 1. And in this case, we'd say it's increasing because it's positive. It's going bigger and bigger. Our 3 is getting triple as big each time. And we have an asymptote line right at the origin. So we'd have an asymptote at y equals 0. So what that means is, at y equals 0, we have a graph. Basically, the graph never goes below it. So that's our sort of our cutoff of the graph. And if we do the 1/3 one, it basically is going to look the same, except it's going to decrease. But we still have the exact same domain and range, still have the same intercepts. It would be decreasing in this case. And we'd have the same asymptote at y equals 0. Okay, the reverse now is we're going to get the graph, and we have to try to figure out what the equation is. So we know with this first one, we can see it's increasing, so we know it's going to be some positive number to the x, and you can see it's crossing at 1, so that's good. So what we want to do now is try to figure out what value it's increasing at. So you can see at when x is 0, we have a y of 1. Let's go to when x is 1, we have a value of y of 2. When x is 2, you can see we have a y value of 4. And if we went to 3, we can see we have a y value of 8. So if you follow that pattern, we went 1 to 2 to 4 to 8, so you can see we're doubling each time. So our equation should be y equals 2 to the x. And if we do this one, we know this one's decreasing, so we know it should be a fraction, something like 1/2, 1/3, 1/4, whatever. So we want to do the same thing. We want to look at when x is 0, we have a y equals 1, which is normal. So now let's go backwards. If we go to -1, we can see in this case we're at 4. And if we go to -2, we can see we're at It looks like it's up here. It's hard to see, but looks like it's around 16. So you can see that as we increase now, we're basically dividing it by 4. We went from 16 to 4, from 4 to 1, and if we kept going at positive 1, we'd be at a quarter, and you can see it's just getting smaller and smaller. So in this case, we're basically dropping. So the best way to do the graph is just look at when x is 1, if it's increasing. So you can see here we went from, at point 1 we're at 2, so that 2 value is telling you what our increase is by. And if we're decreasing, go back to negative 1, you can see we're up to 4, so that just means we're decreasing by 4 times as much, or 1/4. Last example is sort of a real life application. So in this case it says we're going to put money in and it's going to double every decade. So that means at time 1 in this case, or at time 0, we put in $1,000, and we know that it's going to double. So our graph would be an increasing graph, so that means in 10 years we would be doubled, we'd be at 2,000, and then in 20 years we'd be up to 40,000, and so on, or 4,000. So we got our basic graph. So you can see here then our equation would be, if we're just starting with our basic amount, and we'll keep this simple, we'll keep it in 1, so we'll deal with thousands of dollars, so we'll just call our starting value 1, not 1,000, and then we're going to call this 1 decade. So to keep our graph simple, we'll just stick with ones. So our y values in thousands, and our x values in decades. Let me clear all this, and let's kind of redraw. Let's redraw our diagram now. So our y is in thousands, and our x is in decades. So at time 0 we have 1,000, and 10 years, 20 years, 30 years, and so on. So our graph is increasing. So we know that in 1 year we're going to double, we'll be at 2,000, and so on. So our equation should be y equals 2 to the x. So the question is saying, what is the value of a $1,000 investment in 10 years? Well, 10 years is 1 decade, so that should be, we've doubled it. So in 10 years we would have doubled to 2,000. How long would it be worth 8,000? So we can use our graph, or just use some common sense. So in 10 years it'll be 2,000, another 10 years it would be 4, and another 10 years it would be 8,000. So that would be 30 years. Okay, or like I said, we could use the graph and see where 8,000 lines up, and it should be at 3 decades. And our last one is, how long would it take for it to be worth 26,000? So if we continue, it'd go from 1,000 to 2,000 to 4,000 to 8 to 16 to 32. So you can see it's going to be somewhere in between the 16 and the 32,000. The easiest way would be just use your graph, trace along to see when our y value is roughly 26, and we should get our answer from there. So from your graph, if we do that, we graph our y equals 2 to the x, we go up to a y of 26, and it looks like, according to my graph, I'm getting a value of around 4.7. So that would be 4.7 decades, or about 47 years. And that's it. So you can see exponential equations work well for anything that's going to increase or decrease. So it could be things like money investments, car loans, anything like that where we get compound interest, or you get things that are going to rapidly double, triple, whatever. And that's all for today.